Check while running around here.
Hello, hello.
Check while running around. Go run to the thing.
Check. Hello, hello. Is this working? Hello? Yeah, this is working. This is it. Yeah.
started. The next team will have 3 minutes, 2 minutes, 2 minutes. You'll only be marked on the additional information that you provide. Yeah. And then after all the teams are presented, the floor will be open for judges for cross questioning. Any questions? Fine.
Good afternoon, everyone. I am Pranava Bharadwaj, and welcome to the Mathematics Mimamsa Deep Thought 2026.
And my name is Srivatsa. Before we start, we'd like to ask the audience to put their phone on silent.
We shall start by introducing our judges for the day. We have with us Dr. Bhaskar Balasubramaniam and Dr. Prashant Arote. Dr. Balasubramaniam is an associate professor in the Department of Mathematics here in IISER Pune. He works on Hida family, special values of L functions, and Galois representation.
Dr. Arote is a postdoctoral fellow at the Department of Mathematics here at IISER Pune. He's currently working in representation theory. We thank the judges for being here with us. We request the judges to pick a chick and determine the first team to answer the question. We will proceed clockwise from then.
So first is IISER Bhopal.
The first team to present is IISER Bhopal. They shall be followed by IIT Delhi, IISc, and IIT Madras in this order.
Keep this with you, sir.
IIT IISER Bhopal, you may choose a question to begin with. OCD.
OCD biologist's nightmare. A centrifuge has n greater than 1 slots for test tubes uniformly arranged on a circle. Tejasvi is a biologist with OCD and has m 1 less than equal to m less than equal to n test tubes with the same mass. He wants to balance these test tubes on the centrifuge, that is, he wants the arrangement center of mass to be the center of the centrifuge. Observe that if m equal to 1 or n minus 1, it is impossible to balance them. Question 1. Show that if m and n are not coprime, it is possible to balance these. Question 2. Show that if m1 divides n, m2 divides n, and the greatest common divisor of n upon m1 and n upon m2 is not equal to 1, then m1 plus m2 can be balanced. Question 3. What are the values of n such that all values of m 1 less than m less than n minus 1 can be balanced? Question 4. If there exist two configurations A and B such that both A and B can be balanced and the cardinality of A times the cardinality of B is less than n, then there exists an orientation of B such that A union B can be balanced together. Question 5. Prove that n is k balancing if and only if both k and n minus k are expressible as linear combinations of prime factors of n with non-negative coefficients. A note, n is said to be k balancing implies that in a centrifuge of n slots, k many test tubes can be balanced. Any doubts from the teams? You have, since there are no doubts, you have 15 minutes to think. Your time starts now. Teams, you have 10 minutes remaining.
Teams, you have 5 minutes left. Teams, you have 1 minute remaining. Teams, you have 30 seconds remaining.
The thinking time is up. I invite IISER Bhopal on stage to present their answer. You have 5 minutes. Your time starts now.
Hello, am I audible? So basically what is happening is, this is a circle. We can consider it as center at origin, 0, 0. So if there are, let's say there are n spaces, what is happening is, if we look at it as in a complex plane, so there are n possible angles, like n possible, this 360 angle is divided into n possible types. So the angle at of every point is basically 360 upon n. This is a possible angle, like this is 360 divided by n, then 360 divided by n plus that angle. So that is how the points are allotted. Now in the first question it is mentioned that show that m and n are not coprime. So there are two cases. Let m and n both be even. If m and n both are even, what is happening is, let's say it's m and n both are evening, then what is happening is we can construct a pair for every m by 2, we can construct a pair here, so that it gets, the center of mass gets balanced at origin. Therefore for if m and n are even, therefore since we can construct a pair, therefore they will get balanced. Now if m and n are not, if m and n are odd, now consider the case if m and n are odd. So what is happening here is, now the points, basically the sum, basically what we are looking at is the sum of these values will of these points will be 0. Basically what we are looking at is, we can always construct such the matrices, the points of to place test tubes in m possible ways such that these sums will be 0. So basically 360, if we take that number of test tubes is odd, so basically the vector sum of this can be constructed such way, there can be possible such way that therefore this will be 0. This sum will be 0. Now if you look at the third question, so what are the values of n such that all values of 1 greater than m, less than n minus 1 can be balanced? Here what is happening here, okay, so here the number of m and n are not co-prime. So if we take all the possible values of n so that m are not co-prime, if we take those values, so the values which come out for us are 4 and 6. For example, the values of n which come out to us are 4 and 6. Why? Because if we take here m can be 2, 3. For 4 it can be only 2. Here it is even pair, therefore it is balanced again. Here if the value of n is 6, if the value of n is 6, then m can be 2, 3, 4. Again 2 and 6 are not co-prime, so therefore they are balanced. Okay, now prove that. Show that plus n. इसके क्या था, एक मिनट रुक.
IISER Bhopal, you have 1 minute remaining.
रुक जाओ. इसका वो है ना. रुक जाओ.
IISER Bhopal, you have less than 30 seconds remaining.
इसको ऐड किया हम और कर सकते हैं.
IISER Bhopal, your presentation time is up. I invite the team from IIT Delhi to present their solution. You have 3 minutes to present your solution. Your time starts now.
This side you are writing the solution for question 1 and 2, and this is for question 3. Shortly he'll explain 1 and 2 ka, and then I'll explain 3 ka solution. This is a valid construction for whenever GCD is, whenever N and M have a GCD greater than 1. A valid construction in which we can place the test tubes.
Yeah. So basically, if you have m test tubes and n test tubes and m like to put in the holes, then and h is our GCD, then I want to claim that 0 a1 to a1 all the way up till h, which is h a1, which is n, is a valid way to place the test tubes by symmetry. This will be the center of mass of this will be at the center, and since we can do this up till a2 minus 1, then our size becomes like the total number of test tubes we have used becomes this was h minus 1, sorry. So this is of size h and this is of size a2, which is why the number of test tubes is placed total is ha2, and all of them are individually balanced, so the total will also be balanced. They are not
IIT
conflicting
Delhi,
because
you have 1 minute remaining.
they're not conflicting because in case a2 minus 1 was greater than a1, then we would not have n greater than m. And as for the second part, we know that let n is equal to kh, where h is the GCD of the divided things n by m1 and n by m2, then m1 and m2 divides k.
You have 30
and,
seconds remaining.
Yeah, so M1 and M2, N by M1 and N by M2 both have H as a common factor, and therefore they are not co-prime. Therefore, these steps and N by, oh sorry, if K is equal to M1A and
IIT Delhi, your time is
M2B,
up.
sorry, then N by A and B are
I invite the team from IISc to present their solution. You have 2 minutes to present your solution. Your time begins now.
So we can solve it like there are two parts. For the first part, we can just think that if M and M are not co-prime, then for even cases we can just look it as distributing it equally among the two. We can just look at in the general case like say n is the GCD or any common factor of m and n. Since m and n are not co-prime, then we can distribute m by n dash case symmetrically among both the sides. For example, for 6 and 4, we can say that 2 is a common factor, so we can distribute 2 on one side, 2 on the other side in such opposite ways of that their center of centrifuge like in center of mass. Similarly, for 6 and 3, we can form an equilateral triangle.
IISc, you have 1
such
minute
that
remaining.
The center again lies in the center of mass. For the third case, there are different cases like for n equal to 2, it's variously true, as 1 less than m less than 1. For n equal to 3 also, it's variously true. My claim is for n equal to prime, other than numbers 2, 3 and 5. You cannot express. say for example 7, you cannot, if you take m as 4
IISc, you have 30 seconds remaining.
and n as 7, you cannot express that. Apart from that, the non-coprime numbers are the numbers which are even or either not prime. And if m and n are not coprime, then it is possible to balance them anyways.
For the backwards way of 5, we have this n by p1 comma n by p2 as 1, and we can so on keep linear combinations. So we can keep taking those linear combinations, and so that is why we'll have that.
IISc, your time is up. I invite the team from IIT Madras to present the solution. You have 2 minutes to present your solution. Your time begins now.
Hello. So for the first question. So we divide the test tubes in set of A, like grouping them by A test tube in each. So there are n test tubes. So sorry, n places. So they are divided into this. Now what we'll do is we'll fill. So in each group we'll fill the first B places with test tubes. So our center of mass. As all these are symmetric, so this will be divided, and the net center of mass will be 0. At 0. And in the second question, so for the second question, if I am taking m1 and m2 both to be 1, what I am getting is, and I am taking n to be 5. So for this example, this is like a counter example. So what I am getting is GCD
IIT
is
Madras, you have 30 seconds remaining.
GCD is 5 of 5 is not equal to 1, but m1 plus m2 is 2 and n is 5. So if we take n3, suppose, so in any way you place the test tubes, you cannot make the center of mass 0. So I think the second question is like there's some ambiguity in there.
Yeah, and we have written the third and fourth solutions of it. So, like for the fourth solution, there is one argument that if A intersection B is balanced,
IIT Madras, your time is up. Do the judges have any queries or clarifications they would like to ask from the teams?
So in IISER Bhopal, like the first part, you didn't say anything about like, hello, you didn't say anything about when the case when m and n have some prime which is not 2, right? Like you mainly talked about both being even, right? So that means the common factor being 2. So can you clarify that?
So basically, if m and n are odd, what will happen is that we can construct a polygon in such a way, in complex plane, we can always construct a polygon in such a way that the sums of the points of the polygon from the origin will be the sum of all the vectors basically from the origin to the points will be when we add all those points, we will get 0. We can always construct a polygon in such a way. When there are n points on the polygon and we have to place m test tubes, we can always construct a polygon where how we can place m test tubes so that it is 0.
Okay. Okay. Huh?
One is even, one is odd. That case is
yeah. So, that they did not. That's okay.
Any,
I had one question. So here, like what? So you said something about breaking it into how many groups?
So groups of A each.
A each. Okay.
Like so, there will be some G groups.
Okay. And like so, you are not using anywhere that G is bigger than 1, right? Like so, where are you using that?
No, because G is a GCD. So.
I'm using it's like it's not co-prime, so it's greater than 1.
Yeah, but you can do the same thing with G equals to 1, right? Then they will be co-prime. So, but you
No, like, because they won't cancel, because they won't be symmetrics. Like, that's why I meant.
Sorry?
There will be only one vector, right? So,
Yeah.
like, they won't cancel each other.
Okay.
So I'm using.
Are the judges done with the queries? Since the judges are done with the queries, I would like to invite members of the question making team to present the solution.
So for the first part of the question, I think the IISER Bhopal team was going in the right direction. If we draw a circle and then evenly place the points about it. And after this, let's say if we have m comma n and they have some GCD as D, we take a prime P which divides D. And since these are all the roots of the unity, so I can represent this as this equation. And what I will do is, I'll start rotating. If I get a particular configuration, I'll start rotating these whiles. How can I do this? Let's say if zeta p represents the root of this, so it will have zeta p square, so on and so forth. These are the roots of unity, and since p divides d, these should also be the roots, nth root as well. I'll take zeta n and multiply each of the elements with this, so we can start rotating these. Yeah, multiply this. Yeah. For the second part of the question, it was said ki m over, what was the? N over m1 and n over m2, yeah, are not co-prime, so there exists some, let's say, D. And we can similarly do the same process for the second part as well. In that it will be some, there exists some A comma B which are, let's say, that belongs to natural number, and these can be written as n is equal to A times D m1 and n. So these will divide each other, and we can repeat the same argument again. For the third part, I'll use some different approach for this. This is also known as the Sylvester's coin problem, which says ki if you have k less than or equal to p minus 1 times q minus 1, where p and q are co-prime, then you can linearly, you can represent this k greater, sorry, yeah. This sum a p plus, let's say, b q in this linear combination form. For this, you can take all the integers n which are of the form meta. What we will do is we take all the elements mod p as n minus jp, and where j is some integer 0, 1, so on and so forth, mod p. And yeah, we can do this, and we can then represent this as form, if I take j as some sigma, and then we can represent n as some, if we substitute all these, we can represent n as some sigma times a1 plus rho times of a2, where these two are natural numbers. Yeah, for the fourth part, you will
Okay, so the fourth part requires that, so it's given to you that there's a configuration A and a configuration B that is balancing. And their sizes are given to be small a and small b. So what you can now do is, so I'm going to write in nth roots of unity notation. So let's say A is, okay, so let's say, so this is, I don't know how to write zeta, I'm writing eta. So let's say zeta A is an element of, eta A is an element of A, and eta B is an element of B. What you can, so let's say I write these two in, so these two are nth roots of unity. If these, so let's say this pair overlap for some rotation. So what that means is, eta A is equal to eta B times some eta n to the power k. Correct? Does this make sense to everybody? Okay. So the thing is, for each eta A and eta B, you can only have one k where they can overlap. So what you, so now we check the cardinality of set A and set B. So what it's given that set A times set B is less than n. Sorry. But and if we take the total number of elements, like if we, so like A cross B, so this is your set. So your total number of tuples that you can make between eta A and eta B. Your set size will be this, and we know it is less than n. So therefore there must exist some k such that by pigeonhole principle you can say that it will have a rotation where you can balance it. The last part of the question requires you to use these and I think some of the previous parts where to show that if there is a if there is a number k and an n, if you have m test tubes and you have n slots, n is k balancing if and only if k and n minus k are can be written as sums of primes, sums or linear combinations of primes. So the way you start is you take case A. Now, okay, wait. First, what you do is you write the prime decomposition of n. So let's say it is P, Q, and then P1, P2, da da da. Let's say I'm writing this as alpha 1, alpha 2, alpha 3, alpha 4, so on. It's a finite one. Now I'm just saying without any loss of generality that P and Q are my smallest primes. Everybody follows? So now the first case is take case A where k is greater than n by 2. Write k, write k, like replace k with n minus k and then continue to the next two. Alright. Case B, take k lies between n by 2 and p minus 1 and q minus p minus 1 and q minus 1. Now again, this is the same Sylvester coin problem that we have shown in part 3. You just use this and you get and you can just do it again. For case 4 or case C, k is less than or equal to k minus 1 times p minus 1. Oh, sorry, q minus 1 times p minus 1. Now, so what you do is you apply induction, or it's not really induction, but I would like to call it induction. So you take the base case. So let's take some prime P1. We know that P1 can be placed. We know you can just divide n by p1 and you can place those. Second, from part 4, we know that pq is less than p1, p2 is less than n, because there are other factors here. So now you can do the part 4 wala case and get the final get to the, so this is, so you can construct a one with a set p1 and one with another configuration with p2 elements. You can rotate one of them such that you can get the final thing. Last part is my induction set, inductive step. What I'm doing here is, let's say I have a set B which I have already placed, which I have already placed. So let's say it is p to the beta 1 times q to the beta 2, so on and so forth. Now, what you need to do is take beta 1, so let's say beta 1, beta 2, so we know that this will, so the sum will be less than this sum. So now just take some prime that divides n, which is not the same, so like if you're taking a prime pj, take the same, make sure it is the exponent here and here is are not the same, as in one is less than the beta j is less than alpha j, and just so you can, by showing that this product times this, oh wait, this is supposed to be k, I'm sorry. Sorry, this is supposed to be k. Huh? Is that k? Huh? 1 second. What is wrong with me? No, this is n, this is n. I'm sorry. Yeah, huh. So I have already balanced this. I can add a qj, or rather pj prime pj to this, because this times this will be less than this, and by showing that the configuration, like this times this will be less than this, the total set, and because the final set will have a, yeah, basically that is how you do it. And you apply induction based on the sums for each p, q and each prime. That's the solution. Yes, what is your counterexample?
Check. Okay, it's still on. Check. Right. We once again have the 4 questions on the screen. I invite the team from IIT Delhi to choose a question other than OCD biologist's nightmare as your directed question.
Cosmic Weaver's Gambit, please.
Cosmic Weaver's Gambit. In a realm beyond time, two ancient entities, Ignis and Kalis, pass the eons by playing a game of cosmic creation. Their game board is the void itself, and their pieces are the nascent stars. They begin by placing the stars in the void, which we can label as vertices. The game is played by placing a star, or if there are 2 or more stars placed, a celestial weaving of their color can also be done, which, in simple language, involves drawing a colored edge between the stars or vertices. The rules of their celestial weaving are simple yet profound. Ignis, weaving the threads of red, goes first. Careless, using the threads of blue, goes second. They take turns placing a star or weaving the fabric of their choice between two stars and coloring it with their color. The sole objective is to create a polygon of one's own color. A polygon, or in formal graph theory language, a monochromatic n-cyclic subgraph Cn, is found when n stars are all mutually connected by n threads of the same color. The first weaver who creates a polygon of size n with this colored fabric attains cosmic dominance. For any fixed n, who would attain cosmic dominance? Is it Ignis, who makes the first move, or Caelus, who plays second? Provide a detailed argument for the answer. Do the participants have any doubts? If you have no doubts, then you now have 15 minutes to come up with an answer. Your time starts now. participants. You have about 10 minutes remaining. Participants, you have 5 minutes remaining. Participants, you have 1 minute remaining. Thirty seconds remaining. Your time is up. Team IIT Delhi, you now have 5 minutes to present your solution. Your time starts now.
So we are basically considering sequences of moves. We are representing making a vertex by a dot and making an edge by a vertical straight line. So we made a small observation. At first we make a initial vertex, then initial vertex made by the red, and then we have to the blue member must make another blue vertex. So at the next step, it is necessary to make at least one edge. So this sequence continues for you can clearly see we have just sequence of triangular numbers one after the another. We just are trying to make some observations. As we can see at the after every two.
So first, Igneous places a, like we are considering a case here. Suppose first Igneous places a point here, then Caylus will have to, so this is for any triangle. We are trying to form a triangle. So first, Igneous will place a point here, then Caylus will place a point here. Then Igneous will join this line. And now Caylus has to place another point because there are no lines to join. So Caylus places a point here. Igneous draws a line over here. Igneous makes this red. So now to prevent a triangle, Caylus will make a line here. So now again another point has to be placed by Igneous. So Igneous will place a point here. Now if Caylus doesn't join these lines, then suppose Igneous joins this line. So now Igneous will automatically win because he can either join this to make a red triangle, or he can also join this to make a red triangle. Caylus has to join these points now. Similarly, now Igneous places another point here. Caylus again has to join these points, otherwise Igneous will win. So now Igneous places up connects these two, so that this is not a triangle. So now if Caylus places another point here, Igneous will join this and again win. So Caylus has to join another line. This graph has to become connected until a new point is placed. Otherwise, Igneous will automatically win by joining a point here and forming a triangle.
Just to clarify, we claim that either draw or win, and that is why we are presenting Igneous' strategy and saying that B, which is the other player, will have to make this construct up until this B6 move, at which he will lose if he wins B6, and therefore it will have to be connected. Whether or not we will win in the connected case is explained by my team.
So basically, once you have 5 points, the graph has to be connected, otherwise Igneous will win.
So we observe after placing a vertex, to make the graph fully connected, the number of edges to be drawn represented by this bar will alternate between odd and even. This we can analytically calculate by induction. So we keep track of if the number of moves required after placing each vertex will be odd or even. So using this, we can generate a sequence for each nth vertex, the cumulative number of moves, if it is odd and even. And we know, start
Igneous kar raha hai.
So Igneous is starting. So if Igneous is to win, Igneous is supposed to draw the last edge, because from Ramsey theory, we know minimum number of vertices which are in a fully colored graph.
1 minute left.
Which requires that at least one player has a cyclic polygon is Rn, n. So if we have R3, 3 equal to 6, this we can using the general principle very easily. This proof can be generalized for any n using this logic.
I guess if you have 5 points and there are 5 C2 possible edges, which is
30 seconds
10,
remaining.
so there has to be at least one colored triangle, one triangle of the same color by PHP. This is not true for 4C2 because that's equal to 6. Once there are 5 points, one has to win. So our claim is Igneous wins.
IIC, if you could wait. Yeah, you now have 3 minutes to present. 3 or 3, okay. 3 minutes to present your solution. Your time starts now.
Yes. So what I'm trying to do is induction case. I'm saying that if we are able to get to a configuration where, okay, so firstly if we want endpoints, we should be able to force endpoints in two different ways. Like if R wants to win, they want to be able to force end polygons in two different ways. So what they'll be doing is, say this is for points n equal to 5, R has been able to get a configuration like this, where the other vertices of C and other points involved, but in the graph you have got something like this. So if you've proven for n equal to 5 say, and you're going to n equal to 6, this is going to be R's turn. So I will take this point, and now next what we have is, okay, R is Ignis and C is Caelius, whatever, yeah. So now, yes. So C will have to connect over here, and then, one second, my bad. Yes, yes, so R can draw a vertex over here. C will have to block these, so C will block these, and we will get to a configuration where you have
for n equal to 3 simplified case, we can prove that Ignis is going to win.
See, 1 minute, 2 minutes.
So for first, Ignis will draw a star, then of course Caelius will follow by a star because there is nothing. Then we draw a line, then again a star because it's not. Now Ignis plays a line, forcing Caelius to play one line because otherwise he will form a triangle. So after that, the game builds continue, and then another star is drawn by Ignis. Now blue, which is Caelius, will draw one more line, trying to form a triangle. Ignis plays a line, preventing it to form triangle and threatening for a bigger triangle to form. Caelius forms a line, and then if we extend this to a bigger figure, Caelius draws, Ignis draws one point. Caelius will draw a line for a triangle and Ignis will block it. Another point will be drawn, and at the end there will be
IIC, your time is now up. IIT Madras, you have 2 minutes to present your solution. And your time starts now.
Yeah, so Ignis is starting first, so he will first draw a vertex, and then Caelius will also draw one vertex, and then we have a red edge, then we will have another vertex, and which Caelius will draw, and red will make this vertex, make this edge, then blue will try to stop this, and Ignis will make another vertex, and Caelius will make another edge, and by this, and by making, then Caelius will make another vertex, and you get Ignis make another edge, so you get some combination like 2.
1 minute remaining.
Like 2 hours in in one in forming one triangle. Like if either we can join this by R or either we can join this by R. So Caelius can block only one of these two. So like Ignis will win when n equal to 3. And similarly, we can just say like if a path is common with some red edges, like if Ignis is able to make a common path and you have some red edges like this,
30 seconds left.
So Kalis, so Kalis can only block one of those, and Ignis can make a polygon of n-sided. And we were also thinking of like if we proved for n equal to 3, so we can just make these sort of triangles so that we can further prove for higher values of n. Like if n is equal to 3, so if it's proved for 3.
IIT Madras, your time's up. IISER Bhopal, you have 2 minutes to present your solution. Your time starts now.
So what we will prove is Ignis will win in all the cases. So there are 3 different ways which we can which we tried. First was Ignis will always have a dominated strategy, which is to say Ignis will always force the second player, which is Callias, to make a move. Which, for example, if Ignis moves this, Callias will have no option but to move this. Ignis will move this, then Ignis will basically draw this line, and Callias will draw this line. So again, now Ignis will try to join these points which Callias is drawing, and then so to block this again, Callias will draw another will try to draw another point here. So to block this. Now to get for a fixed n, what is happening is there are 2 ways Ignis can win for a fixed n. First of all, if there is a polygon which exists which has n plus 1 sides, which has let's assume n plus 1 sides. So if the diagonals, that polygon is formed with the same color, then Ignis can join the diagonals of these points and
Less than 1 minute remaining.
The end point, basically excluding one point and joining this point and forming the polygon of n sides. That is the one way. And second way which Ignis can win again by what IISc said is that another point that if there are n, the second way is there are
30 seconds remaining.
there are 2 polygons. There are two polygons, not polygons, but not joined vertices of these points, and these 2 can be the points. So for that point, again, Ignis is always winning. So since from here, by this cyclic loop which is formed here, when Ignis will force this cyclic loop, this will form a cyclic
IISER
loop.
Bhopal, your time's up. Do the judges have any questions?
Okay. So can each of you finally just summarize your claim in just one sentence?
So for any given n, we are going to calculate our n comma n and find the cumulative number of nodes for that.
No. Just like a one line, like a.
The answer will depend upon r n comma n. I'm explaining how we can get the answer from r n comma n.
So you're saying you just say does it depend on n, or so is there a winning strategy and does it depend on n? Like that's so just like a one sentence, like a quick answer.
So for 3,3 Ignis will win, but we are claiming for a gentle n. Sorry, could you repeat what we are required to answer?
Like a very short answer, like what does it depend on? Because a lot of you, I mean, there is a lot of information, but I just want like a condensed answer. Like what is the final answer?
So for different values of n, if r n comma n will correspond to cumulative odd, Ignis will have a winning strategy, and if it corresponds to cumulative even, then Keles will have a winning strategy.
Okay, all right. Next.
Claiming Ignis.
Our claim is Ignis is good for all. We've just proved for n equal to 3, which is a base case, and then we applied induction there.
So you're saying Ignis will win all the time?
Yeah.
Okay.
N equal to 3 base case and then applying induction.
Okay. All right. What about you?
It will go infinitely. If Ignis do something, Kelis will always oppose it, and then.
You're saying Kelis will always win?
No. They won't reach any conclusion. I'm saying.
Okay, it will be like an.
It would be sort of a draw type situation.
Okay, all right. And you said it will Ignis will win. Okay.
Do you have any more? Do the judges have any more queries?
No.
Then I invite members of the question-making team to present the solution.
Hello, am I audible? Okay, nice. Do I have colored chalk? Get a red and a blue.
Also, we can state most of them are wrong.
Hmm?
Because Ignis will not win n is equal to 3 case.
Okay. Hello. Yeah, everything. Yes.
So for most of you guys who said Ignis will win all the time, that's not correct.
Yeah, so basically it just depends on the parity of n. So I'll just give the final answer first and then I'll go over the proof of it. If n is even, then player 1 will win, which is Ignis, and if n is odd, then player 2 will win. So here is the detailed argument. Again, I think some team, I think Madras itself had an argument where they created a structure like this. Essentially, your what I call a winning structure is similar to this. But then for n equals to 3 case, this is your usual winning structure. But when n is general, you just have a structure like this. Essentially, it's a path of length 2n minus 4, and then an edge in the center. So each of these have length n minus 1, and this is just an edge. So when this structure gets created, then even if blue tries to block one of the edges, then you can just join this. Sorry, this needs to be n minus 2, and then you can complete a Cn. So your objective is to create a structure like this, where each of these are n minus 2 as the player who's playing it. I will do 2 claims first. So again, the first claim is that it's inoptimal to place a new vertex when your graph is not complete. So that is what IIT Delhi actually managed to figure out. So let's say you have a length of path k1 for the first player and a length of path k2 for the second player. Now I'm playing as the first player. If I just place a new vertex, the second player can extend another vertex, increasing his path length to k2 plus 1. And that is kind of inoptimal because you need to create this structure. So the bare bones version of this structure is basically a path of length n to n minus 4. So by if you add a extra edge, then that just means that he's increasing his path length, and because the objective is to get to a structure like this, you can't really do that. Again, now that doesn't really tell much, but combining it with the next claim, it makes sense. So the next claim is that if both players play optimally and a Kn gets formed, and both players play optimally, it implies that both players will have a path of length n minus 1. Now again, we prove this by induction. The base case is, again, like you just take n equals to 4 and then you can just start this by playing optimally. So the first player places a vertex, second player, first player. Then the second player plays again. First player places a vertex, second player does that. The first player plays and then the second player plays. So K4 is formed now, and there are 4 vertices. Now you can always already see that there is a path of length 3 for blue and a path of length 3 for red as well. So for n equals to 4, the claim is true. Now assume the claim is true for general n. So n minus 1. If it's true for n minus 1, you have a complete graph kn minus 1 and paths of length n minus 2 for both players. Now the graph is complete, so obviously the next move would be either player to create a vertex, and because both players are playing optimally and they need to increase the length of their total path, you just join a vertex. Now if you are not the first person to join a vertex, let's say you are playing red and blue tries to block one of your paths, you already have the other vertex, you can just increase that to get your path up to the next, length. So this claim is true by induction, that in Kn you have paths of length n minus 1 for both players. Now going back to that, let's say you have a graph k 2n minus 3. So what happens in this case is that both players will have paths of length 2n minus 4. But then as soon as the graph kn minus 3 is complete, the next player to place a vertex will be in a losing position, because then let's say if blue places a new vertex, red can just extend this and that creates his winning structure. And then later, even if blue tries to block one side, the other side you can just join it and win. So again, technically the only thing that matters is who is the last person to complete the K4 in some sense. Now again, we can calculate that using the number of edges in K2n minus 3 plus the number of vertices. Again, there are 2n minus 3 vertices in K2n minus 3, and there are 2n minus 3 choose 2 many edges. Now if you calculate this number, it comes out to be 2n square minus 5n plus 3, but we aren't really interested in the actual number. We only need the parity of it, because we need which player completes the K2n minus 3, which comes out to be n plus 1. So now if n plus 1 is odd, then the first player completes the K2n minus 3, which means he can add this, his opponent has to add the new vertex, which means he can create his winning structure. So when n plus 1 is odd, player 1 wins. And when n plus 1 is even, player 2 wins. Okay, so any doubts?
Yeah, just to add to Richard's point here, you can just basically after that will determine who is dominating here. So winning after this will just involve 4 moves. So you'll just play the vertex somewhere around here, and then you'll play this. The dominating player will basically play the central edge to the center of the path, and then you can essentially, because you have 2 terminating positions or 2 peripheral positions, you can just play one where, and then essentially you have a winning strategy.
IISc Bangalore, you may choose whichever question you want to answer. Retirement home? Okay.
retirement home. A new immortality retirement home is founded by Gosman Hernandez, with him as the inaugural member. Starting from day one, exactly one new member joins and no member ever leaves. Every member is also permanently and unchangeably part of a club, which is decided on the day of their induction. A new member is either inducted via a celebratory ceremony or is quietly inducted. If the new member is quietly inducted, then the new member joins the club of whoever they meet first in the retirement home. There is an equal probability of meeting any of the existing members. If the new member is ceremoniously inducted, then that member creates their own new club. The probability of a ceremony happening on a given day is T. Define f of n comma t as the number of clubs with exactly n members after t days. What is the probability of f of n comma t being 0 as t approaches infinity for a given fixed n? You may make use of the following hints. The expectation value of a random variable x is defined as e of x is equal to the sum over chi of x of chi times p of x equals chi, the Stolz-Cesaro theorem as stated, Stirling's approximation as stated, and Azuma's inequality as stated. You have 15 minutes. Do you have any doubts? You have 15 minutes to think up solution. Your time starts now. 10 minutes remaining.
Participants, there is a typo in the printed sheet in Azuma's inequality, but it's correct on the slides, so please refer to that. Instead of f in comma t in your sheets, it should be f n comma t. It's correct in the slides, you should refer to that.
5 minutes remaining. One minute remaining. Thirty seconds remaining. Participants, your time is up. I invite the IISc team to present this solution on the board. You have 5 minutes to present your solution.
Hello.
Your time begins now.
Okay, so first I'll find a bound for f of n comma t plus 1 minus f of n comma t. This is the difference between the number of clubs that have n elements on the t plus 1th day as compared to the previous day. So there are let's say there are x clubs there's some clubs with n minus 1 elements, some y clubs with n elements. So there are 3 cases here. Either if the new person joins a club which has n minus 1 elements, then this would become 1. If it is like, if they join some other club out of these 2 options, or they form their own club due to a ceremony, then this would be 0. And the third case is that this is minus 1 if they join a club with n elements. So this would become n plus 1 and it would go out of the case. So if we look at the modulus of these two, this quantity, it's very clearly bounded, is less than or equals to 1.
We have observed that the distribution of the number of clubs will be a binomial distribution of sorts. So the probability that you have k clubs at time t is p to the power p to the power k minus 1 minus p to the power t minus k minus 1, and t choose k minus 1. So it will follow a binomial distribution.
Right.
Yeah. And the expected value will be, sorry, I'm writing.
P to the power k minus 1 times
so this is
p to the power k minus 1 minus p to the power just this t minus k minus 1 tc k minus 1.
If using this we are able to get the number of people per club, if we are able to get an expectation value of that, then we can further use Soham's argument. We can approximate that, and then we can use Soham's argument to be able to conclude.
This argument, this thing.
Basically, we can use this one,
your number of into k, this into k, sorry, multiplied by the number of clubs in a given day. Okay. So yeah, the probability that there are there are n people in a is going to be just this total summation, which is just going to give, if we remove k, the summation will be 1, and the probability that you have n people at the time t is just going to be your is going to be this term, which is going to be oh no, this is going to be 2 to the power t, and this is going to be p to the power k minus 1 into 1 minus p to the power t minus k minus 1 into t choose k minus 1, and from here we can get that the expected value of the okay, so if our random variable is the total time t at which we have people, so
1 minute remaining.
At which we have okay, no, wait, one second. No, it's fine. This is fine. I'm just cooking.
we can use that then from this inequality f of n comma t plus 1 minus f of n comma t less than or equal to 1. We can use Azuma's inequality and the expectation value to find that this expression is going to be less than or equal to 2 exp to the power minus alpha square by 2. And I mean k is equal to 1. So It's by 2, sorry, it's alpha square by 2, 3, so from here it's done.
I invite the team from IIT Madras to present your solution. You have 3 minutes to present your solution. Your time starts now.
Okay, so like for this question, we start our approach with defining f of nt, which is number of clubs with exactly n members after t days. So now we are interested, according to the question, in limit t tends to infinity f of n comma t, and we are given that p is the probability of a person being ceremonially invited. So for any club xi, if I define, for any club ci, if I define my pi of the person entering the club, and I assume that my clubs have member x1 comma x2 comma dot 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 xn, then pi will be xi divided by summation of xi into 1 minus p, and for a person to be ceremonially invited, he'll create a new club anyways, so that will be p. So now for my transition from n minus 1 members in a club to n club, I'll find my expected value according to this equation. So first I have n minus 1 f of n comma t minus 1. Transition from n minus n members, number of clubs with n members at time number of the time. I have a third term which I'll add and the new member club of n comma t minus f of n comma t. I have my transitioning from n comma t. This is the second term which is transitioning from n to t minus 1. This is the number of clubs, and this is n people inside the club. My probability of meeting this n people is n by t minus 1, and 1 minus p is my probability of becoming
And for n equal to 1, what we have is we can have another group of team size 1, club size 1 if he is doing by probability p. If a new club is made. And for that, for n equal to 1, we won't have any n minus 1 case.
And once we find all the the expected value of e of f n comma t, so we can by this Azuma's inequality we can derive the probability of we can derive the probability when f and t becomes 0 as t approaches infinity. So this was the recurrence relation that we were we thought of.
And we can use the limit condition to prove that for the probability of f of n comma t equal to 0 as t tends to infinity.
IIT Madras, your time is up. I invite the team from IISER Bhopal to present their solution. You have 2 minutes to present your solution. Your time begins now.
Okay, so first we will do is create a recursion formula for the probability. So let p comma nt be the probability f comma nt is equal to k. Let this be the probability. Now for a general n comma t, this is equal to p n comma t minus 1 plus 1 minus p n minus 1 c1 p n minus 1 t minus 1. Now, why is that? Every day only one member is added. So there is a chance that that one member does not has its own inauguration ceremony. So that way the clubs with the same number of n will not increase. Now there is a second case when that guy enters silently. In that case, to increase this probability, this guy will have to will not the probability of not having this will not having inauguration, and also meeting all the members of the t0 to n minus 1 t minus 1, so this will be n minus 1 c1 of meeting out of n minus 1 c1. And now we will expand this using a base case. When we expand this using a base case, we will get a binomial summation, which will look, if you take t minus 1, it will have this n t minus 2 and this n minus 2 c1.
IISER Bhopal, your time is up. I invite the team from IIT Delhi to present their solution. You have 2 minutes to present your solution. Your time begins now.
So we are dividing the total number of we are dividing the teams into 4 cases. One of the cases is the number of teams that have more than n members. One of the teams that have equal to n members, and the rest 2 are as n minus 1 members and less than n minus 1 members. So we are trying to find the recurrence relation between values of the number of teams, expected value of the fn and fn of t and fn of t plus 1. Expected clearly, as we can see, the expected value as we move from fn comma t to fn comma t plus 1, we are just considering the 2 cases.
1 minute
in one case there will be a ceremony where the probability of ceremony occurring is p, and that one of the members meeting a member is from one of the team is from the team that has exactly equal to n members is equal to sigma of all the members in that of all those members by the total number of members. And
30 seconds remaining.
Similarly, for all the 4 cases, we can calculate the probability of the new member meeting the given any of the people from the chosen set, and the final probability that the new member does not have a new ceremony will be 1 minus p into total number of people in that.
IIT Delhi, your time is up. Do the judges have any queries or clarifications?
So in the first one, what is the closed formula again? Can you? So that is IAC. The closed formula, the final one.
The ET of k, or the probability that there will be a team with n members?
No, the
which formula?
The final probability, yeah.
Okay, I think, yeah, the 2 to the power t in the denominator is incorrect. That should not be there.
No, it's for 2 times what?
Oh, okay.
In the box?
Oh, that 2 e to the power minus a square by 2t.
Okay, e to the power minus a squared by 2t. Okay. But where is n in this? Like, what is, I mean...
What?
So there's no n here. What is a?
A is independent of n.
No, but what is a?
That is the I think that is, but it's supposed to say that the probability of mod of f of n comma t minus equal to a then 2 to the power e minus a square by 2 k minus 2. Sorry.
Okay.
What is your final answer?
We didn't calculate the final answer.
Like we saw the inequality, like the Azuma's inequality. So like in this, we need to calculate the expected value of fn comma t. So we first try to find out the recurrence relation of e of fn comma t using e of fn minus 1 comma t minus 1 and e fn comma t minus 1, and using the base case of n equal to 1, we can calculate the expected value of fn comma t, and like putting the value of the calculated e of fn comma t as t tends to infinity,
we can calculate the probability like using the inequality, using the Azuma's inequality. So that's what we tried.
Oh, you are
We
saying
didn't-
something is 0 or something like that.
No, we didn't calculate the actual, like exact answer, but we just like tried to solve the approach. Yeah.
Do the judges have any more questions? Since the judges are done with the questions, I would like to invite member of the question making team to present the solution.
Okay, so as most teams figured, like the way to solve it is using a recursion. So I'll try to keep this as short as possible. So shorthand, I'll just firstly just for shorthand notation, I'm going to use ENT in place of this. So as IIT Madras showed, what you get for En t plus 1 minus ENT is just En minus 1 of t times 1 minus p n minus 1 over t minus En of t 1 minus p n over t. This is just the same thing that they have written. Now I'm going to introduce a new term called Cn. Cn is just the limit as t tends to infinity of Ent over t. Whether Cn converges or not, we'll come to that in a while. But if you will see, Ent here, this and this will go to Ent. This will also go there. So what we get here is lim t tends to infinity of En t plus 1 minus En t is equal to just Cn minus 1 of 1 minus p n minus 1 minus this becomes Cn times 1 minus p times n. Now this term, I'll just put one thing here, t plus 1 minus t, this is just 1, gets cancelled out. Now here we can use the Stolz-Cesar theorem, and this will just become lim t tends to infinity of E n t over t, which is just what we defined our Cn to be, and the rest, the right hand side stays as it is, minus Cn, 1 minus p. From here, if you put the terms here then there, what you will get is a recursive equation for Cn in terms of Cn minus 1, which will be, one sec, 1 minus p n minus 1 by 1 plus 1 minus p n. Similarly again for n equals to 1, that, sorry, is it better? No? No? I'll just hold it. So let's find it. Okay. Again, for n equals to 1, you have a slightly different equation here. Here you get get A1t, this P minus E1t 1 minus P 1 by T. You use the same idea for you use the Sidhar's theorem again, do the rest of the thing. You'll figure out that C1 is equal to P by 2P. So what we have figured out here is P C1 is some non-zero finite number, and from this recursion we can also figure out that all the Cn's subsequently are also going to be some non-zero finite numbers. So now what we are going to do is we are going to shift this guy there. It is T tends to of T tends to infinity. Now, equality now, as we figured that as this change that. So if you use the inequality says f n t minus e n t being greater than or equal to a is less than or equal to exponent minus a square by 2t. K is here 1 obviously. Now we want to convert this part into fnt equals to 0. So when does fnt become 0? When this term is going to deviate from the mean term by a value of by value of en by plus t, en of t. En of t, as we figured, is as for large enough t is of the form Cn times t. So our A here essentially becomes Cn times t. So what we want here is Cn of t equals to 0. The exact same thing, we just replace A by C of t. Now we get 2 exponent Cn square t by 2. Again, this thing blows, t goes to infinity. These are constant normal terms. This is a normal term, like constant finite number. So this thing blows up to infinity. Sorry, there's a minus sign here. This thing blows up to infinity. This becomes minus infinity. E to the power minus infinity is 0. So this thing becomes less than 0. And since the probability it has to be at least 0, so we get to know that this thing is exactly equal to 0. Hence, fn of t not being 0, the probability becomes 1. Now coming to showing that Cn exists in the first place. So what we'll do here is we'll do induction. We'll show for n equals to 1, and then we'll go from there. So let's say our E1t is some constant times t plus some error term. What we want to show is that this error term goes to 0 as t goes to infinity. And in particular, the constant term we want here is p by 2p, since that is what the value of C1 we figured out. Now, if you take this and put it into this equation, and then you just solve it, then what you will get is, so by reiteration, you will get that delta of t plus 1 is equal to delta of 1 of t 1 minus p by t. Now this t, now you can write delta 1 t in terms of t minus 1, t minus 2, and so on up to some arbitrary t naught. So what you get by multiple recursions is that you will get delta t is equal to delta 1 some t naught times, you keep multiplying this every single time. So you start with k equals to t naught to t minus 1 of 1 minus alpha by k. Alpha is 1 minus p. In fact, I'll write this in a better way. This becomes k minus alpha by k. Now I'm going to divide these two in terms of k minus alpha and k separately. So this just becomes delta 1 t naught. Now I'm just going to write this in terms of gamma function. So k minus alpha, you start with t minus 1 and then t minus 2 and so on up until t naught. If you write this in your gamma notation, this will just become t minus alpha by gamma of t naught minus alpha. And you do the same for this guy. It will just be on the opposite side. This will become gamma of t, and this will become gamma of t naught. This is a constant term, this is a constant term. We'll ignore these guys for once. Now this guy and this guy, if you use Stirling, so this entire part, just call it k for now. And these two terms, by using Stirling's approximation, you will get that this is approximated by t power minus alpha. Alpha is a positive number, so this so as t goes up to the power minus alpha, this thing goes to 0, so this will approach 0. So that's how you get that C1 exists and is in fact of this form. For the higher for the inductive step, you just have to do pretty much the same thing. Instead of 1, now you'll use that equation, and you just you do the exact same thing. You put the equation, you substitute from the recursion equation, you substitute this term here, here all the in terms of Cn minus 1. And then eventually you'll find the same thing. It's again mostly calculative, so I get the point right. So, so using that, we show that Cn exists and converges to what value we figured it out, and from that the rest of the proofs follows. Yeah.
It is now time for the directed question to IIT Madras. You do not have a choice since all the other questions have been taken. Therefore, we will proceed with the question Sarok ka sapna.
Sapna. Consider the integers 1, 2, all the way to p minus 1, where p is an odd prime. Now we square each number modulo p and take those as our new starting set. We continue this process infinitely many times. Question 1. Show that the above process stabilizes in a finite number of iterations. Question 2. What is the size of the set it stabilizes to? Now take an element chi of this final set. Consider the set of elements obtained by repeatedly squaring it modulo p. Question 3. Show that this forms a loop. After some iterations, it will come back to chi. Question 4. If p is such that the size of the final set is a prime, let's say k, what are the sizes of these loops? Can you comment on how many loops we will get for a certain size? Note, you will not get marks for solving the red questions, only fame. The questions in red are question 5. What about a general p? Now, we had taken the qth power of each element instead of squaring it, q is a prime, what would you get for question 6, the final set size in terms of p and q? Question 7, the sizes of the loops in the final set. You may use the following hints.
Just a note, for the red questions on the print, the order of question 5 and the statement is given in reverse. You may follow the one given in the slides. Doubts? If you have no doubts, then you have 15 minutes to think about your answer. Your time starts now.
Participants, you have 10 minutes remaining. 5 minutes remaining. Participants, you have 1 minute remaining. Thirty seconds remaining. Your 15 minutes are up. It's time for presenting. IIT Madras, you now have 5 minutes to present your solution, and your time starts now.
So first I'm proving the third part. So we took an element x and we need to prove that this element forms a loop and will come back to x if we repeatedly square it. So now we take a set x square, x power 4, this is x power 2 power 2 up to x power 2 power p. Now, so I'm proving by contradiction. Suppose not I is like all these are different modulo p. But as we know, there can be only 0, 1 to p minus 1. There can be at max p different modulo p possible. So take this with p plus 1. Yeah. So now, so from this set, at least two values will be equal. This means, suppose xi n equal to xj mod p, x2 power I equals to x2 power j mod p, then we'll have a cycle.
Yeah, so for the first question, what we are doing is, if we have the first sequence as 1 to till p minus 1 and we just square it, so as the cycle length is finite, whatever operations we do of squaring, it will only result in in a finite sequence. And if we can just prove by contradiction, like suppose it's not the finite number of iterations, suppose there are infinite number of iterations to stabilize the, or you can't stabilize the process, so we can definitely get a cycle, as the cycle length is finite, we can definitely get back to the same number and just continue from it. So it gets stabilized to a finite set. And as asked in the second question about the size of the set, suppose we get a cycle length of, like a minimum cycle length of L. So what we got is the size of the set should be the size of the set should be the smallest cycle length plus 1, because like repeating that cycle, like iterating through that cycle, and the initial is the starting point, so it will take around L plus 1 distinct terms in the set.
So another argument is that if I have numbers from 1 to p minus 1 and I square it in mod p, then I'll have my numbers from 1 to p minus 1 only, and my size of the set will still remain less than p. So like for, we have worked out some examples, then we can see that if we get some palindrome sequences, like for a number, for a particular permutation in ascending order, we'll get the stabilization after squaring and mod, we get a palindrome, and then if it stabilizes, it will be such that it forms any cycle, and then this argument is valid for question number 2 and 3 as well.
Yeah, and one more point, this term, like OXN, which is the smallest m, such that x bar m is 1 mod n, it should be the cycle length of any sequence, like 1 till p minus 1. So we can just say like OXN is the smallest, is the smallest cycle length that we can get, and based on that,
1 minute remaining.
and there was one more observation, that 1 and p minus 1 belongs to the same cycle. So at the last, we can just, as we are iterating through the cycle, 1 and p minus 1 will correspond to the same term in the set.
And for the examples of p equal to 3 and 5, we don't have a cycle because my 4 is mapping to 1 and my 2 is also mapping to 1. So when I get something like this, when one of the number is mapping to 1, then I'm sure that this set will be stabilized, because 1, 1, 1 will still map to 1, 1 after that. So, which one? Since we said this in the first argument, if I have something which is not a cycle, 3 goes to 4, 4 goes to 5, something like this, then I'm sure that this case will not happen, and it will eventually stabilize, proving from this argument.
IIT, your time is up. IISER Bhopal, you now have 3 minutes to present your solution. And your time starts now.
Okay, so in the first question, the numbers are 1, 2, 3, 4, 5 to p minus 1. So if we square these numbers, we will there is a chance of getting a number which is greater than p and less than p. So and if we mod these numbers, since mod gives us remainder, so the numbers which we'll get is between 0 to p minus 1. So basically what is happening is from this sequence the number of since this set includes all the remainders of the p when divided by all the remainders when divided by p. In this set the number will be less or equal to this set. So after some time this set will reduce, and since the set is reducing, after some time the numbers will repeat or will have a palindrome sequence. So this will form some kind of stabilization. Now for the second question, the size of this set is basically the prime number is taking p by 2, and this is the lowest integer function of p by 2. This will be the size of this set. Also
1 minute remaining.
Okay. Also for the third question. Okay. For the third question, let's assume a number a which is in this set. So if we take a, what will happen if we square this and take a mod? Since the thing is that this number is getting stabilized in the first place, after multiple stabilizations, after multiple iterations of this stabilization, it will basically try to. Why it will happen again? Because here this number of size is greater, and here the number of size is less. That is because some remainders are repeating, and since some number are repeating in the same set, therefore in this x will after some time will loop back to x, and therefore will repeat.
IISER Bhopal, your time is up. IIT Delhi, you have 2 minutes to present your solution. And your time starts now.
So first we have a solution for question 1. We'll present 2 methods. First is the method that after each iteration, after every time we perform the operation, the set size either decreases or remains the same. If it decreases, it will decrease to greatest integer of n by 2, because if a is congruent, if a and minus a are both there, then a square will give the same value again. So both of these to just 1. So we are strictly decreasing set of sequences. So it either goes to eventually 1 or it will stabilize. Another proof which is like direct. So basically we can have p minus 1 factorial plus 1 combinations of the set. P minus 1 factorial combination of the set. So if we perform this operation p minus 1 factorial plus 1 times, then by PHP at least 2 of the modular sets will be same. So if 2 are same, then obviously it has repeated. So now it will repeat again, and now we have
1 minute remaining.
And we have some results regarding the size of the set. So first off, p minus k whole square will be congruent to k whole square mod p, because p is congruent to minus k. Therefore, the size will be less than or equal to p minus 1 by 2, because the symmetric ones will get the same congruence. Another condition is that if it has to decrease from p minus 1 by 2, then we can take the list of a square, and if a to the 2n is congruent to b to the 2n, then this condition must hold. So we can check for each of the n by 2 C2 combinations whether or not there exists n such that a to the 2n plus b to the 2n is divisible by p, and that is the number of things which will reduce. No.
And for third question,
another thing about one result we got about the fourth question is there will always be greater than or equal to 2 loops for k greater than 5, because the loop for 1 will always exist, and then for the rest, as IIT Madras claimed that.
Third also, IIT Delhi, your time's up. IISc, you now have 2 minutes to present your solution, and your time starts now.
So for the first one, we can show that it's finite iteration. We can take some examples like 1, 2. After we square it mod p, the stabilization is from 1, 1 for 5. If we square and do the mod, first up will be 1, 4, 4, 1, and then it stabilizes to 1, 1. For 7, the stabilization will be similarly 1, 4, 2, 2, 4, 1, and 1, 2, 4, 4, 2, 1. And for 11, it will be around like 1, 4, 5, 9, 3, 3, 5, 9, 4, 1, and so on. So based on these observations and using the fact that the number of sets will be only from 0 to p minus 1 where p is prime, so it will go to stabilize. For 2, the claim is the size of the iteration will be p minus 1 by 2 to the power k, where k is some number such that 2 to the power k is the highest power of, it divides p minus 1, but 2 to the power p minus 1 doesn't divide. So yeah, 2 to the power k divides p minus 1, 2 to the power k minus 1 doesn't divide this. For example, the size, if we compare versus size table, for n equal to 3 it was 1, for 5 it was 1, for 7 it was 3, for 11 it was 5, for 13 it was 3, and so on. For the third one, we can simply show that once you get the iteration, say for the seventh one.
So for the fourth part, we have G is a generator, so order of G comma P is 1. There's a bijection between the powers of G, so this set mod P minus 1, and the numbers 1 to P minus 1, and this set. So we have G to the power alpha into 2 to the power k is equal to G to the power alpha. So alpha into 2 to the power k equal to alpha mod P minus 1. This is because otherwise we'll get a order is smaller, and hence 2 to the power k to the k is congruent to 1 mod p minus 1, and hence the answer is order of k mod p.
IISc, your time is up. Do the judges have any queries or clarifications?
Since the judges do not have any questions, I'd like to invite Saroj from the question making team to explain the answer.
This works? Okay. Yeah, so in the first part you have to show that this sequence stabilizes in finite number of steps. So there are two important hints. First of all, Fermat's little theorem, which says that a power p minus 1 is congruent to 1 mod p. And the second hint is given that you can assume that there's some n less than p, some number between 1 and p, such that order of what is the condition? What? Order of n mod p equals to p minus 1. Now this essentially says that if you consider, like if you follow n around this process, you'll get something like n, n square, and so on until n power p minus 1, which will be equals to 1. And you can see that if you take some n power I equals to n power j, where I is not equals to j, then like you have been given that this order is defined such that this is the smallest number. So you can, like if you have something like this, you can cancel that out and you will get that order of n is something smaller than p minus 1, which is a contradiction. So all of these have to be distinct. Now that you have gotten a number such that all of these are distinct, and there are p minus 1 of them, so you can basically think of them like one of them is 1 and so on, and this basically gives you all the numbers from 1 to p minus 1. They are of this form. Now what you want to look at is what happens when we square. So the main point here is that when you are modulo p, so p minus 1 for example modulo p, it's basically just minus 1. When you square it, like if you were to square p minus 1 like this and remove the terms that are multiples of p, you'll essentially just get 1. So this is congruent to 1 mod p. And that's the main observation in the first and second parts of the question, that when you have an element here that can, an element that's basically a square root in some sense of minus 1. Essentially, so here we have n to the power p minus 1. We want an element in between such that it's of the form n to the power p minus 1 by 2. And if there is such an element, now when does this exist? This is when p minus 1 is like divisible by 2. So when you have such an element, then any element of the form n power p minus 1 by 2 plus k and n power k, these are, both of these things will go to the exact same square because this squares to just 1. And that basically tells you that whenever 2 divides p minus 1, your set size will reduce, and basically you will get alternating terms like elements from this set. And so long as 2 keeps dividing your new size, for example, later it becomes p minus 1 by 2 or p minus 1 by 2 to the power some k, as long as 2 can divide this set will keep reducing. But p minus 1 is obviously a finite number, so 2 can only divide it finitely many times, and hence this process terminates. And this, what was the second question?
Set size, final set size.
Oh yeah, this basically also gives you the final set size because it's basically, where k is the highest power that divides p minus 1, highest power 2.
Third question, Ken? Ask question, yeah. So now we start with an element x in the large set, final set. We keep squaring it. X square, x to the 2 to the nth. Now, I want to say that, okay, so first of all, these will all be part of the final set. So they have to be eventually periodic, but this can become like here. I am saying this has to come back here, specifically here. That's the question. So to show that, so this will eventually come back here. So let's do it. X to the 2 to the I equals to x to the 2 to the j. It will eventually happen for some j, I and j. I have to show that I equals 0. Then just let's say without loss of generality, take I less than j. Now x to the 2 to the I times x to the 2 to the j minus 2 to the I minus 1 equals 0. So either this is 0, which is not possible because primes, or this is 1. This is 0. That means x to the 2 to the I times 2 to the j minus I minus 1 equals 1. You can see the fact that this is x to the power some element whole to the power this, some power of 2, that is going to 1. That is not possible in the final set, because in the final set we have removed all such elements that square or to the power 4 to 1. So this is a contradiction unless I equals 0. Because then we don't have squaring. We have just x to the power 1. So yeah, so we see that they all form cycles. Now note that 1 forms its own cycle. It cannot go anywhere else. For other elements, so let's take another element x. We want to say x to the 2 to the n equals to x. We have to find the lowest value of n such that this works. Again, subtract. Just subtract and invert. 2 to the n minus 1 equal to 1. Now this tells you something. But look at here, x. What is the order of x? Like, what is the minimum integer such that if I take power of n, it becomes 1? Again, as we are in primes, this n is actually just p minus 1. Oh, no, sorry, not p minus 1, sorry. My mistake, it is just k. The final set size, because it's prime. Because if something else, if x some other less n divides it, we would get that n would divide p. So if x is not 1, then n has to be k. So I keep speaking p. Yeah, this k. That means this whole number has to be considered modulo this k, because of the fact that x powers of x loop after k. So mod k is equal to 1. We have to find the smallest n such that this works. What is this number? Now we see this has to be as x equals 1, and this is equal to x equals to the power 0. Then that means 2 to the power n should be congruent to 1 mod k. And we want the smallest n such that this works. So by definition, n becomes O2 k. Okay, so now how many cycles? And you see, as also we started with a prime number set. The final set is prime sized. There is no virtual difference between the other elements. Like you can take any one of them, they would behave the exact same. So that means all of the cycles have the same size except for one. One is its own cycle, and as I am saying, the other cycles are length this. Sorry, this is cycle length. This is the total number of elements. The cycles are disjoint, they cannot intersect. That means this is the total number of cycles. Okay. Do I explain the red part? Do I? Okay, so if the final set size k is not a prime, it's still pretty simple. Now this x, this odd, we write mod k here. This cannot be mod k. This can possibly be all divisors of k, d, right? D divides k. We write all divisors of k. That's important. Now we just take the same thing, d, same thing. Now finally the answer becomes for a certain divisor d of the final set size k, you have a cycle of odd size O2d, and its length would be the number of order d elements in the final set by this. This was the reason why we did not put it in the main portion. Yeah, this would be, it is the Euler-Torsion function. This would be the number of cycles of this size contributing from this d. Now it might be possible that this number can be same for two different d's. Let's say d1 and d2. Then you just add. You just add here because the bottom number is the same. Just add all factors such that O2d is the same. Then add. That will be your number of cycles. We put the, I think that instead of squaring, we do powers of q. Yes, same question. There is literal no difference, because when you start, you get n square to n to the p minus 1. When you square, you get all just that's the even powers. When you take qth power, you just get all multiples of q. All multiples of q or multiples of q square then and continue. So in that case, the answer would be just p minus 1 by q to the power k, such that q to the power k plus 1 does not divide p minus 1. And everything, you replace 2 with q, your 2 here with q, exactly this. So yeah.
That brings us to the conclusion of Mathematics Mimamsa Deep Thought 2026. We thank you all and hope you enjoyed the round. We will be back with Earth and Climate Science Deep Thought shortly.